Hello dear students, this is experiment on V by F controlled induction motor. So here this is the drive, V by F controlled drive. It's a Toshiba made drive. You can see its number, and you can download the data sheet from internet for this drive. Now this box is containing this drive and some terminal connection arrangement and the metering arrangement, and then some on off switch and protection. So there is nothing inside this box. Whatever you are seeing at this front panel, those are the things. And this drive itself contains the controller as well as the display, these two buttons, run button and stop button. Then there is also a variable button, and you can also see the connection terminals and other terminals which are at the back side of this. Okay, so here are the terminals for connection, and on this door the names of the terminals are also written. So generally in industries, these terminals are used to connect this drive to the PLC or any other control equipment, and then data logging, or you can say SCADA. So all that arrangement for connection is here. So this is an industrial grade drive which you may see in some industries when you start working in industries. Okay, now this is 3-phase inverter. It is having 3 legs, and RYB are the 3 output terminals. Basically it is converting DC into 3-phase AC, and you have already studied the V by F control scheme, the block diagram. So in that we have to provide frequency as an input, and then whatever is the voltage required to maintain V by F ratio constant, that is automatically calculated by the microcontroller, and then that voltage will be produced using PWM, and that PWM pulses are given to the inverter for operation. Inverter is also there inside, then a rectifier is there inside, controller is there inside. So why rectifier is required? So this DC bus is created from the single phase AC which is given through this plug to this kit. So this is a basically you can say a 3-phase induction motor drive, and input to this is single phase AC. And again this is a drive of you can say European standards, not American standards, because it is 240 volts. So it is producing a 3-phase voltage of around 200 volts. Okay, 3-phase. In India, 3-phase is 440 volts, but this drive is producing 200 volts because it is designed for that 110 60 hertz AC system, which is normally there in USA. Okay, so I'll tell you how to operate this. Actually, when we open this, there are settings. Okay, so this mode button is there. Mode button easy button. So using these we can set so many parameters in this drive. Means we can set highest frequency which is 60 hertz normally, but if we want to limit speed to some value, in that case we can set that high frequency, highest value of frequency, which will be equal to or less than 60 hertz. Then we can also set acceleration rate, deceleration rate. We can enter the parameters of the motor so that it will be very good in understanding the, you can say, motor performance. And like that, there are so many functions inside. Again, this can communicate with the PLC or SCADA and all of that. So when you go through the manual of this or datasheet of this drive, then you will come to know what are the capabilities of this drive. Now operating this drive is very simple. What I will do, I will directly set a frequency. Okay, right now it is 60 hertz, and then I'll just push a run button. Okay, then see, slowly the motor started to run, and you can also see how the voltage is slowly being increased. So you can hear the sound of the motor now, and you can see the voltage increasing. See, it is going up to 100 now. So like that, we have set the frequency to 60 hertz, but it is slowly going to 60 hertz so that it is doing a soft start of the motor. So it is acting like a starter. So whenever we are using any drive, in that case we should not be using any other extra starter. Okay, otherwise it will be of no use. So whatever is this thing used for speed control, the same thing should be used for starting purpose also. Okay, now you can see frequency is approaching to 60 hertz and voltage is approaching to more than 200 it is. Yeah, so right now frequency is 60 and voltage is 230. 230 volt 3-phase AC as per the American standards. So motor is running with full speed. Okay, now I will vary the frequency knob and we can observe the voltage, and we have to plot the graph between frequency and voltage. We have to see the variation. As we know that in V by F, the ratio V by F is kept constant when the speed is between 0 to the rated speed, and beyond rated or mostly the beyond synchronous speed, if we want to have the speed control, then we cannot increase voltage, we have to just increase frequency. So that capability must be there inside this drive. The controller must be programmed in that way. Okay, so we'll just take the readings of F and V and we'll just plot. So I'm reducing. We can reduce it in any steps. We have to go up to 0 hertz like that. So I'll just initially reduce it with 5 hertz. So it is at 55 right now. See the voltage, 215 around. Okay, this is the voltage. Just keeping the camera horizontal. You get the exact reading. Okay, almost it is 215. The next will be 50 hertz or 50 hertz. You can see the voltage is 200 volts. Now for 45 hertz. You can see the voltages almost 185. Okay, 185. Next is 40 hertz. You can listen the sound of the motor to note that its speed is reducing. Okay, now for 40 hertz. Check out the voltage. It is 150. Then I will just go to 30 directly. Okay, 30 hertz. For that, the voltage is 135. Then I directly go to 20 hertz. So for 20 hertz, voltage is 100 volts. Then 10 hertz. For 10 hertz, see how slow the motor is running. This is the beauty of VBAF control. Okay, otherwise normally when we give just 25% of the rated voltage to the motor, it runs with almost full speed. Okay, see the voltage. Voltage is just around 15 volts, like that. And now I directly go to 8 hertz. So it hertz, the voltage is around 10, and then 5 hertz. Hertz, speed of the motor, very low. This is the voltage. Okay, so this way you can control the VBAF. So I have kept the acceleration very slow. So now you can see, even though I am increasing the frequency very fast. Okay, now I have gone to 60, but see this motor is not gaining speed. So acceleration rate is set to very low value. That is why it is increasing its speed slowly. See the voltage rising. Okay, in that way you can control this drive and plot V and F and check out how is the variation, how is the relation. So that's what the today's experiment is. VBAF controlled 3-phase induction motor drive. So I have plotted the readings in Excel, frequency versus voltage. So first column is the frequency 60, 55, 50, 45, 40, 30, 20, 10, 8 and 5 hertz. Voltage we got 250, 215, 200, 185, 150, 135, 100, 15, 10 and 8. So the ratio VBAF is 4.2, 3.94, 4.1, 3.8, 4.5, 5 and then 1.5, 1.3, 1.6. So I have plotted frequency on x-axis and voltage on y-axis You can see it is not a very straight line. That means the ratio is not perfectly constant, but still it is in a range. So we can say it is around 4 when the frequency is between 60 up to 40. So 60 to 40 it is maintained at 4. Then between 40 and 20 it is maintained at around 5. And then between 20 and 10 it is drastically reducing. And less than 10 Hz it is just 1.5. So not intended to use it below 10 Hz like that. Now why this ratio is not perfectly maintained at 4 or like that? This ratio is not perfectly maintained because it is very difficult to decide the PWM duty cycle using programming. So they have done it approximately, they have maintained it approximately. So that is not an issue. Okay, it is changing very little bit only. So if I just round off this column, see this, the ratio is 4 4 4 4 4 and then 5 5 and like 2 1 2. Okay, so it is almost maintained as 4 up to this 40 Hz and then 5 up to 20 Hz. So generally this range it is used, okay, always or many times. Therefore here it is exactly maintained. So this is what the result of our experiment, and whatever I have discussed